to another episode of Uncertainty and Probability Theory, the logic of science. And I thought I would do it since there was a lot of questions I'm getting mostly by email about p-values and all this kind of thing. I would do a wrap-up. I'm not going to introduce too much new, but except for one thing. This has always been my statement: never use or trust a p-value or confidence interval or any of those things. And you shouldn't even rely too much on parameter estimates, as we saw last week. We're going to be doing all these things in regular models. We're going to go through all of these in real models and so forth. And today I'm going to try to go very slow. And it's not even going to be a long class, I don't think. But I want to emphasize a point which I have forgot to emphasize about p-values before. I have said, and it is true, that there are no consistent frequentists. Frequentism is the theory that probability is a real thing. It's a property of the world, a property of nature. Nature has true distributions from which it draws things. You'll hear people say draw things. And all of these must be embedded in an infinite sequence, or at least a hypothetically infinite sequence. And there are certain rules and theorems in frequentism which are stated. Mathematical proofs are given in its name, and all those mathematical proofs are correct, given the premises which they embrace. But the interpretation invariably is wrong. And I've tried to prove that to you time and time again. But an interesting thing about frequentism is you cannot have a hypothesis have a probability. A hypothesis is a statement, is a proposition. Now, we built from day one the idea that propositions in logic, because probability is the completion of logic, propositions given certain evidence can be certain or uncertain or anywhere in between. They can be certainly true, they can be certainly false, they can be in between. In other words, they could have probabilities. If they're certainly true, then we have at least a local truth of some kind. It becomes a necessary or universal truth. When the premises of whatever argument you're using, whatever evidence that you're having, is itself necessarily or universally true, and all the way down on back to the axioms or your intuition, or rather your intellection, the inductions that we use by intellection. We did all that from the very beginning. And that's how people who call themselves frequentists actually behave, while denying they are behaving that way. And I've proved that to you before, and I'm going to prove it to you again. And I'm going to bring up the one thing, I kind of brought it up in a slight way, but I did not emphasize it enough. And so this is sort of like a review of what I should have said more clearly. But every one of these classes I do, I try to squeeze in. Originally it was supposed to be 10 minutes. That didn't work, and I'm trying to squeeze them into 30 minutes. And I end up talking very fast. I understand this. Get excited about these things, start waving my arm around like an enraged monkey. And maybe sometimes the point gets lost. So what we want in science and life is we have some proposition. We'll call it H for hypothesis, whatever you like. We have some evidence that we assemble. That evidence can be whatever we entertain. So is it going to rain tomorrow? That's a hypothesis. It will rain tomorrow. Will it or won't it? We don't know for sure unless it depends on the evidence that you're going to assume. You might have some kind of meteorological model in there. You might just be basing it on your knee, or the time of, the pain in your knee or something, or the time of the year, whatever. Everybody will have a different set of evidence, and that evidence can include, it will certainly rain tomorrow because I said so. Well, the probability that it will rain tomorrow given the I said so is 1. That's a true probability, a true deduction. Whether that's a useful model, your model is on this side, all the evidence is your model, remember that. So will the new drug work? That's a hypothesis. Will the new drug cure twice as many people as the old drug? That's a hypothesis. Will the particle emerge from this experimental setup spin up? That's a hypothesis. Whatever we like. whatever hypothesis that we want, any proposition that could be observational or not. In science, it's observational hypothesis for the most part, but it doesn't have to be. We assemble the evidence, and that includes all of the evidence, the implicit or tacit evidence of the words and the definitions and the symbols that are used. All that is part of the evidence that is assumed. We write this very compactly in this cartoon equation here, but in any given judgment that we make, there's a whole host of things. In informal judgments we make all the time, we often have the evidence coming in and out. It's changing rapidly. It's not fixed or anything like that. So it can seem probability is a little uncertain or something, itself uncertain. But that's only because we're not fixing the evidence. We learned that once you fix the evidence, whatever that happens to be, and you have this proposition here, and then it's a deduction after that. Probability is just a deduction, just like logic is, because this is logic. That's what we want. We always want something like that. We want to know whatever, you know, does this new pill cure depression? There's an example of it. Or what, so that means you have to have a definition of depression. And that has to have all its ambiguities noted and so on and so forth. We do this. Everybody wants this. Now, here's the way classically, this is the probability, this is the p-value. We learned that. We learned that we're calculating the probability of data we did not see or have not seen. Typically, it's stated data that's more extreme than we saw, which is data we did not see, assuming the hypothesis is false. That's the p-value. That's the p-value. We did this. Now, this is nuts. It's a perfectly, all the calculations that people make are correct, I'm sure. There's a lot of people making a lot of mistakes out there and a lot of cheating going on. I'm not counting any of that. I'm not counting a mistake. I'm talking about people who make these calculations correctly. They have this hypothesis here. They say it's false, and we calculate the probability of data we did not see. And if the p-value is less than the magic number, we reject this null hypothesis, which means we accept this hypothesis up here, which given all the evidence we have implies that the probability of that thing is 1. So frequentists start by saying you cannot have a probability on a hypothesis, and then they go ahead and make one. They don't say that they're making it. They don't actually write it down. They don't write this probability of the hypothesis given the evidence it has equals 1. And they don't even believe this. When they reject these null hypotheses here, which is the contrary, logical contrary of this hypothesis, they more or less think that the smaller this is, the more likely this is true, which means this is some number, some number itself. We'll call it the Q value, if you like. This is some number Q. And they can be very vague about what the value of that thing is. They basically won't give it a number because it's forbidden to give it a number in frequentist theory. You're not allowed to do this in frequentist theory. But everybody does it. Everybody uses this p-value as evidence something like this is true. We did Fisher's example of this. He said either we've seen this small value by chance, or this hypothesis is in fact false, which means this one has to be true because it's the logical contrary of it. It's nuts. Why not just calculate what you have right there? Why not just calculate this directly, openly? Here's all of my premises. Here's my model. Here's my data. Here's everything I'm assuming. I'm calculating this. Now, you as the reader don't have to agree. You don't have to agree with the evidence. You don't have to agree with the model. You don't have to agree with the rest of the premises. But you could check to see whether or not, if those premises hold in real life, that model has any value. We'll learn how to do all that in the future. Again, this is what happens. The smaller this p-value is, and you'll see people, they'll print tables of p-values, and they'll give an asterisk, which means it's just smaller than the magic number. Or they'll give 2 asterisks, which means it's a little bit more small than the magic number. Or they'll give 3 asterisks or something like this. Or they'll write, as we're going to see, they'll write something like p less than 0.001. Oh, that's really small, which means this thing is really going to be false, the null hypothesis, or very likely false, which means that thing right there has a very high probability. Now, all that's forbidden, but that's what everybody does, okay? Everybody does that. Now, here's the one thing I did not do. We did a spurious correlation. We did one of these before. This is from Tyler Vigen's site, if I'm pronouncing it Vigen, if I'm pronouncing that name correctly. Spurious correlations, look it up. It's the first thing that always comes up. The guy's got well over 1,000 of them now. It's a lot of fun to look at some of these things. Here's one, just happened to pop up, one of the first ones today. I didn't spend a lot of time picking these out. This is, you could look at the exact one. It starts out at 1975, goes to 2020 or something like this. In white here, it's the popularity by some index of the name Annabelle, the number of girls who are named Annabelle, baby girls born. Okay, it's a thing you can measure. And then in red here is the number of UFO sightings in South Carolina. Now, these have different Y scales, the popularity of the name Annabelle and the UFOs in South Carolina. It doesn't matter. But if you were to do a test, the hypothesis test on this, we would assume that the null hypothesis is that they have nothing to do with one another, and everybody always thinks causally, even though that's forbidden in frequentist theory too. They think causally about the name, what's driving which. They don't say which is driving which. There's the UFOs retreating in South Carolina, and they were giving people Annabelle rays or probes and telling them to favor this name for whatever their nefarious, extraterrestrial purposes are. I don't know. But that's the idea. So one of the null hypothesis is that these have nothing to do with one another. And we got a p-value. I didn't calculate this. He did, and I'm sure he did it correctly. All the other ones I've checked seem to be done correctly. He wrote it like this, p less than 0.01. Which would give us 2 asterisks in these normal tables of significance. Oh, highly significant, they would call it. Highly significant, meaning this thing has a high probability. That's what they're implying, but not stating, not writing down. They're not writing it down, but that's what they mean. They could get away with denying it. I don't really mean that. Well, then what do you mean? That's the key here. That what do you mean if you don't mean that? Well, they mean this thing is really false. Well, if that thing is really false, the logical contrary of it must be really true. All right? You can't escape the logic of this. So this whole idea of using p-values is nuts. Why not calculate this? Just why not calculate this? We don't need the parameters we could use inside models. I'll show you how to do all that kind of stuff, but we don't need the parameters. They're not interesting to us. What's interesting are these propositions that we want to entertain. Are the theories that we're using true? This is the theories and the models and everything go into here. And do they make good statements about the world, which we can test? That's how we should be doing it. This is absolutely how we should never be doing it. But here's the real point I want to make. Here's the real point I want to make, and which I did not emphasize before. We look at this, and he's got, like I say, he's got 1,000 of these things on his site or more. Generating them all the time, just crunching through various databases and finding things that stick. It's a lot of fun. I think it's a lot of fun. People will look at this. Frequentists, people who claim they're frequentists and who calculate p-values and so on, will look at this and they'll say, ha ha ha, this is silly. This is obviously silly. I think it's silly, and I agree that it's silly because I'm doing this. I'm doing this, and I'll explain what I mean by this. Well, if they claim to be frequentists, and they claim to be beholden to p-values, in other words, they claim that the logic of p-values is correct, all right, and useful. And they have, every time I do these anti-p-value things, people come back at me and say, but Briggs, yeah, I understand that you've proved that every use of a p-value is a logical fallacy, because you can't move from this to this. You cannot move from saying this HF is false to concluding this has some high probability or something like this. It doesn't, you can't say, you cannot assume HF is false and then conclude this. Based on this data you not see. We prove that every use of a p-value is a logical fallacy. There's just no argument about this. It is a logical fallacy. But people still use them, and they'll tell me, Briggs, I understand what you're saying about all that logical fallacy stuff. I get it. But p-values still have some uses. They can still be useful. Because look at what I found here. Look at here, though. Okay, Well, let me ask you this. This vegan Tyler has over 1,000 of these, like I said. And this particular one we'll just use. They're all pretty much the same like this. We reject as goofy. I reject as goofy. I think it's silly. It's not proof. I have no necessary proof. I say, given everything I know about UFOs and the popularity of the name Annabelle and so forth, I think the probability that there is a causal connection that UFOs are causing Annabelles or Annabelles are causing UFOs is extremely low. I'm not saying it's zero, but I'm saying I can't prove that it's zero. But I'm saying the probability is extraordinarily low. Here's the problem with the p-value people. This is what I didn't emphasize. They have to accept this. They have to accept this. They have to say, yeah, you're right. There is something going on. These are linked. UFOs, sightings in South Carolina, and the popularity of the name Annabelle are linked. They show an association. Increasing numbers of girls named Annabelle increases the risk of UFO sightings in South Carolina. That's another way they'll say it. Or it increases the odds of seeing UFOs in South Carolina. All these kinds of words are used. They have to. They cannot. They have nothing else. If they say, I'm rejecting this because it's absurd, because there's no causal ties between these things, which I agree is true, then they're doing this. And if they could do that for this, right there, do it all the time. Why have this intermediate step of these p-values here, which are just plain wrong, fallaciously wrong? You do that to every one of these spurious correlations that are in there. And the idea of the p-value is, well, if you embrace the magic number, which is 0.05, you know, only 1 out of 20 of them will involve making an incorrect decision. all 1,000 some of his are the incorrect decision. But you'd have to accept every one. There's no falsification of this. There's no falsification in here. If you wanted to go that route, there's nothing falsifying anything in here about this supposed causal connection between these two things. You have to, if you are a true believer in p-values, you have to stick with p-values for everything. You can't just write down a probability or or make statements like this. If you do, then you're rejecting the idea. I shouldn't use the word rejecting because we use that technical rejecting language in here. But you're giving up on p-values and you're embracing things like this. I really want people to tell me whether or not they get this, okay? Because it's extremely crucial. If you're going to be consistent and you claim to hold with a theory, frequentism and hypothesis testing and all that kind of stuff, then you should be using this result as claiming this is true and write a paper on it. You should be able to write a paper on it like you've written every other paper you've written when you found these kinds of correlations. Or this is a correlation and with a low p-value, when you've rejected the null hypothesis. If you reject this, you're saying this thing is false or very likely false, which means this must be true. So why not just calculate this? It's absurd that this is right. We could just write this is absurd because there's no possible causal tie, and here's my evidence of that. And you could say that the probability of this hypothesis is unlikely, which means the probability that this is true, HF is true, given that same evidence, is high. All right? You could do that. You already do that because when you're throwing these things out. But if you're going to be consistent and say p-values have uses, then in fact use them everywhere or don't use them at all. You can't pick and choose the times that you're using a p-value because you can always do this. So why do p-values at all? Now, where are p-values used? They're not used in things like this. People would never even think that, except for in his joking manner that Tyler Vegan does here. He calculates p-values for these things. But people never would. They wouldn't even calculate a p-value in this case, which means they're going tacitly in this direction. If you accept the logic of p-values and the theory of p-values and you claim to hold it's true, the theory is true, then you must do that for every piece of evidence that you have. You can't just choose and pick and choose and take some like this and take some and use them in the p-value situations, where you're going to use p-values in some situations and not in others. You have to use them in all situations, but it's not done. It's not done. Why isn't it done? Where are p-values used? You see p-values used in sketchy situations. In sketchy situations in which you're not quite sure what's going on. We're not really sure if there is a causal connection. The author almost always wants there to be a causal connection. Sometimes they want the opposite of that. They want to say there's no cause between whatever x and y that we have here. But usually they want to say there's a cause. And so they can't get to this point. They can't claim the probability of the hypothesis, the causal connection that they want, is in any way probable, given whatever evidence that people are willing to believe. So they go this p-value route. They're not thinking like that, but they go the p-value route because they don't even think about starting at this particular point. They just use the p-values because that's what everybody else does. And you see all these p-values in use in these sketchy situations where you don't believe it. I have on my site, wmbriggs.com, wmbriggssubstack.com, looked at hundreds and hundreds of papers over the years that have these wee p-values, which are obviously preposterous, which should have been recognized as preposterous, but weren't, because the p-value says reject, and therefore we're accepting this, which means there's no way out of the logical conundrum. It's an absolute morass, and I can't see why I'm not making people see that. I am failing. I am obviously failing. I've tried to make these points clear. I've written several papers of this. I have it in the book. It's, of course, it's in Uncertainty. I have all these points, and including the one I'm making today that's kind of shiny. And I'm giving you in fact, I've given you almost the entire book here. I left out some of the boring bits online, so you didn't even have to buy the book. You could read all this stuff. I'm not the only author who makes points about p-values and shows their shortcomings and their fallaciousness and all that kind of a thing, but it doesn't stick. And why? Because it's fecund. You give this Tyler Vegan proves it. He just throws a bunch of data sets that he found online together and finds what sticks using p-values. You could prove hypothesis, in air quotes, prove hypothesis after hypothesis after hypothesis endlessly using this p-value stuff. All right, it's just easy. And he's proving how easy it is. Thousands of these things. And they're all ridiculous. And we know they're ridiculous because we judge like this. But it's the same thing when the scientists do these kind of things. Now, what happens when an honest scientist who is carefully regulating his experiments and controlling them in the proper use of the word control, not in that statistical nonsense use of control, which means I threw everything in a regression. That's not control. That's just silly. But real control, like a chemist would, I'm going to titrate this, I'm going to put in exactly this amount of molars of whatever this and that kind of thing. And they're very careful control, making sure all the heat, there's no excess extraneous heat from all these different sources. Real control. Now, they do their data. They're very careful about, they have a suspect causal relation, and they more or less confirm that causal relation by the experiment that they've done, in the control that they've done. They've more or less confirmed it, but haven't necessarily proven it 100% true, haven't proved a necessary connection in the sense of a necessary or universal truth. They haven't done that, but they've come pretty close because they've been so good about their controls and so forth. And in a lot of those cases, they'll get a small p-value. And so they come to think that the p-value then is therefore confirming what they already knew, because the p-value is therefore small. And in a lot of those cases, not all of them, but in a lot of those cases. And so they'll come to say, yeah, there is something in a p-value. It's telling me what I want to know. I mean, I've confirmed more or less my causal connection that I have in all this kind of a thing, or the theory I hold. And the p-value is small, and that's what I see. And these careful scientists then come to think, yeah, there must be something to all this. But it isn't true. It's still a fallacy. What they're really doing is this. And they're noticing the correlation between, high probabilities of this and low probabilities in calculations like this but it's just a correlation, and it's not a causal correlation. It's just, again, uh, just because of their well-designed experiments and so forth. But if they could do well-designed experiments, why not just, again, calculate this? Show us all the stuff that you've taken in your experiment. All that stuff goes in here. I first gathered this much milliliters of that chemical A, and then this much of chemical B, and the heat was this, the pressure was this, and on and on and on. Boom, 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 boom. Here's all the evidence, and here's what happened. Probability is high. Just calculate that probability. We can all, and then anybody who wants to check that model and has the facilities to do so and so forth, they don't even have to have the original data. They can just follow the steps. That's the way a lot of the scientific fields operate, right? They just follow the steps and they see whether they can reproduce the phenomenon. That's the way the so-called hard sciences operate anyway. So I'm asking all sciences to operate like the hard sciences operate. I'm asking them to act like we could really measure reality, and not all this waving hands and mumbo jumbo about rejecting null hypothesis and all that kind of a thing. So I hope I've made it clear with all the previous 3 or 4 videos we did on all this. I'm sure I haven't. And I'm going on the correlation that as many times as I've spoken about this stuff, I still can't convince people who are diehard p-values to give them up. They just won't do it. So I'm open for all suggestions that you guys have, that we can help others come to see the truth of these kind of calculations. But I think it all comes down to, in the end, it comes down to those basics about probability. I don't believe probability is a part of nature. Probability is not ontic. It has no ontological state. It's purely epistemological. It's merely a matter of our mind. It's a measure of information that we have, given whatever we assume. And it's purely epistemological, and that's it. There's a fundamental divide in those beliefs, however. And that is what drives these p-values more than anything, because here you're giving some kind of probabilities about data, and data is alive. Data has been drawn from nature with probabilities and so forth. So you're calculating something that's real, they think, about the world in these probabilities. But it's not true. It's not true. We did that from day one. And in order to convince people of that, we have to go all the way back to the beginning and look at all those arguments, which we painstakingly built up over like a 2-month period before we even got to the real probability calculations and so forth, just going based on just strict logic and building all that up. That takes quite a while to do. And it's never taught that way in any kind of probability class or statistics class that I know of or heard of. And I can't get away with teaching this stuff in any real classroom, which is why I'm doing it online, because it's absolutely forbidden to do this kind of a thing. Well, not at this level. Perhaps I can get away with a seminar or something like this, but you can't teach the kiddies this when they're coming up through Stat 101 or Probability 101. You're not allowed to do this kind of a thing. That's absolutely forbidden, because people still believe in this stuff. All right, that was only supposed to be 10 minutes, and I went a half an hour. Again, it's mostly review, except for the one idea that if you're going to say you say their p-values have uses, then you have no grounds to reject this. You have to accept it until you redo the experiment and find it isn't true. Good luck with that. Let us know how it turns out with this and the other over 1,000 that Tyler Vegan has. Redo the experiments with gathering more data, and we'll see how it goes for you. All right, that's it for now. WMBriggs.com, WMBriggs.substack.com, and thanks for listening.